In this section, we continue the solution of linear ODE differential equation using Laplace transformation. We take the example of this full chlorination problem. Where there are two streams, F1 in, F1 out, F2 in, F2 out. And we had this V1 and V2. For this specific problem, we'll consider that V1, V2, meaning the volume of liquid in the two tanks, those are constants. Meaning the volume and the level of liquid in the tanks are not changing. Okay. Now we consider the chlorine concentration here. So we consider this to be C1, this to be C2. The chlorine coming in here was C1I. This was C1. This is C2I. This is C2. Now we took a simplified approach to consider that this C2I is 0, meaning there is no chlorine coming in through the second stream. And we wanted to find out a model between C2 and C1I, meaning if there is a change in the chlorine concentration here in this stream, what will be the dynamic change in C2? For this case, we derive the first principle model as dC1t over dt plus F1 over V1 C1t equals C1it. This was the component from the component balance equation in the first tank. And for the second tank, we get the similar equation, dC2t over dt plus F2 naught over V2 C2t equals so now here this F1 are nothing but we consider that F1i equals F1o, so we had used the notation equals F1. Okay. Now I want to write this equation in a simplified or standard form. There is no linearization required because there is no nonlinear term, but you can express those in a standard form as, if I simply make this coefficient to be 1, so we'll have C1t here, and to make it 1 we'll have to multiply everything by V1 over F1, so we'll get equals C1it. Okay. The same thing, if we make this coefficient to be 1, we'll make this coefficient 1 by multiplying with V2 over F2 naught. So this will give us will be here F1 over F2 naught C1t. Okay. Now we'll use this notation that we will consider this to be what is our tau I and what is our tau 1, and this will consider the coefficient 1 to be k1, and we'll use this to be tau 2 and make this notation as k2, and then we'll try to solve it. So we have in the standard form, instead of writing V1 over F1, we'll write as tau 1 dC1 over dt plus C1t equals K1 C1it. So we'll write as and this one will be tau 2. So these are the two equations we are supposed to get at the end of step 4. The equation in their standard form as linear ODE. Now let's see how to solve this equation to get the solution, meaning that expressing C2 as a function of time. Okay, definitely for a given input value, meaning that definitely for a given C1IT. Okay, to do this again we'll use the Laplace transformation approach, and if we take the Laplace transformation of the first equation, so that's what's our defined as step 5 in the modeling exercise. If we take the Laplace transformation here, for that equation we have tau 1 So we'll use the notation Laplace transformation of C1t will have C1s and s. And later we'll see how to express this C1is. So if we do this, we know that for this Laplace transform, the derivative becomes s C1s for this term, and tau 1 being constant, it goes out. We'll have tau 1s C1s plus C1s equals K1 C1is. Okay. With further simplification, we can write it as C1s will be K1 over tau 1s plus 1 C1is. Okay. Exactly the same way, if we look at the second equation, we'll be able to get something like C2s K2 over tau 2s plus 1 C1s. Okay. Now from here we get that if we replace C1s by this equation, K1 over tau s plus 1 C1is, we'll end up getting something K1 K2 tau 1s plus 1 tau 2s plus 1 C1is. Now if the concentration here changes, suppose it changes in a step manner, meaning it had got some value at the beginning. So if this is our what is called as time 0, just for our case, when you start the experimentation or whatever, we consider the time limit. That time can be considered as 0. Suppose at some time it was, say, at some value 10 or so, or it changes to 12. So the change in C1i, that's 2. Okay. Now here one thing note that we express the equation in the deviational form for this case. Now we don't use the notation the prime, because from now on all the variables we'll be considering will be in their deviational form. So just to keep the notation simple, we'll not be using the prime anymore, but definitely those will mean the variables in the deviational form. So we have C1it here, it's really 2. Suppose we take any value m, delta naught, meaning that before time 0 it's 0 and after time 0 it's m. So for this case we'll get C1is to be m over s. Okay. So using this notation, at the end what we get, C2s will be, and if we use this K1 K2, if they define to be simply K, will be Km over s time tau s plus 1 tau 2s plus 1. Okay, so we get the expression for C2s like this one. And how to get the expression in the time domain, that will require the use of what is called this inverse Laplace transform. Now for this case, to get it back to the time domain, if you know the inverse Laplace of this entire term, we can directly get it. Or if you don't know the inverse Laplace of this term, we can use the partial fraction expansion to express it as summation of three different terms, and you can take the inverse Laplace transform to get the expression back in the time domain. For doing that, we'll write it as suppose Km over S is some constant A1 S plus some constant tau 1 S plus 1 plus some constant tau 2 S plus 1. Now how to find the value of this constant? That's the approach called partial fraction expansion. So from here we can write that Km equals A1 times tau 1 S plus 1 times tau 2 S plus 1 plus A2 S plus A3 S tau 1 S plus 1. Now to evaluate what are the values of this A1 and A2 and A3, we can plug in putting S equals 0. This will give you the left hand to be Km, and these two terms will be 0. So we'll have A1 times 1. So A1 is equals Km. Now to find the value of A2 and A3, now let's for this case suppose put S equals negative 1 over tau 1, or this term is tau 1s plus 1 equals 0. We'll end up getting on the left hand side Km. The right hand side, this one will be 0 and this one will be 0. So A2 times negative 1 over tau 1, and then this one will be negative tau 2 over tau 1 plus 1. So this will lead us A2 to be Km tau 1 squared over tau 1 minus tau 2. Okay. Similarly, putting S to be negative 1 over tau 2, we'll get the value of A3, which will end up to be negative Km tau 2 squared over tau 2 minus tau 1. Okay. So now from this we get that C2S equals this summation of these three terms. So we'll end up getting C2S Km. All this term has Km in there. We'll have 1 over S minus A2 over tau 1s plus 1. So we'll have tau 1 squared, tau 1 minus tau 2, and 1 over tau 1s plus 1 minus A3. So tau 2 squared, tau 2 minus tau 1, and 1 over tau 2s plus 1. Okay. Now if we take taking inverse Laplace transformation, so the left hand side will get in the time domain expression for C2. So C2t will be the Laplace inverse of, so this is Km, constant remain outside. The Laplace inverse of 1 over S. So you can use directly from the table that Laplace transformation of a constant equals the constant over S. So Laplace transformation of a constant over S is the inverse Laplace of the constant over S equals the constant itself. So it's 1. And for this case, this one means a constant, tau 1 squared, tau 1 minus tau 2. We can have Laplace transformation of 1 over tau s plus 1 is simply 1 over tau 1 e to the power t over tau 1, and then this one will be tau 2 squared, tau 2 minus tau 1, become 1 over tau 2 t over tau 2. Okay. Just for further simplification, we can get Km 1 minus, so you have tau 1 over tau 1 minus tau 2 e to the negative t over tau 1 minus tau 2 over tau 2 minus tau 1 e to the minus t over tau 2. So this is our final expression for C2 when there is a change in C1t of this equation. So for a given C1it, this is the expression for C2t. So that's what is the solution of this equation, and we use the Laplace transform approach to get the solution. Important thing to note that you have to have the idea about this partial fraction expansion, because we do not know the inverse Laplace of the entire term. We use the partial fraction expansion to express the equation in a simplified form, summation of 3 different terms, and we take the inverse Laplace of these individual terms.